In this video, we're going to round off our coverage of alkene addition reactions by talking about how to predict the products of alkene additions in general and apply them in synthesis, particularly in multi-step synthesis of relatively complex products. Let's start with predicting the products of alkene additions. We're going to consider three key questions here to predict the product when an alkene is treated with some electrophilic addition reaction conditions. Number one, what are the identities of the groups being added across the double bond? We're going to look at the reagents and consider what groups within the reagents will be added to the carbons of the double bond. Then we're going to consider the regioselectivity. Do we expect Markovnikov type addition or anti-Markovnikov type addition? And is there a regiochemical issue at all? In something like halogenation, there is no regiochemical issue. Ditto with dihydroxylations. And then we're going to consider the stereochemistry and the stereospecificity. Do we expect syn addition, anti-addition, or a mixture of the two, leading to diastereomers or enantiomers, for example? We want to avoid memorizing the outcome of each reaction here. Instead, applying chemical reasoning and generalized problem-solving strategies to reason about what is most likely to happen under each set of reaction conditions that we come across. One thing that can help with this is grouping mechanistically analogous reactions. One way to do this is shown on this slide. We can put hydrohalogenation and acid-catalyzed hydration together because both of these reactions involve an open carbocation intermediate derived from proton transfer to the alkene by a strong acid. And that carbocation is susceptible to rearrangements, stability trends of carbocations, and all that fun stuff that's helpful in predicting products. Halogenation, anti-dihydroxylation, these reactions involve a cyclic three-membered ring intermediate and no open carbocations. So they display anti-stereospecificity because of this opening of the three-membered ring occurring via an SN2 mechanism and things like this. So those are mechanistically analogous to each other. Hydroboration and syn dihydroxylation similarly form both new bonds in one elementary step, but do so in a syn manner. So they're stereochemically analogous, these two reactions. The two new bonds to the alkene are added at the same time and from the same side of the alkene. Thinking about these analogies between different mechanisms, as I've mentioned previously, makes it a little bit easier to manage the massive amount of information associated with all the reactions you'll learn in your organic chemical education. Grouping in this way will help you become a more efficient problem solver as well. Let's practice predicting the products of some alkene addition reactions. So here we have this alkene. It's almost symmetric, but not quite. Notice we have an ethyl group on one side and a propyl group on the other, with these two methyl groups connected to the two carbons of the alkene. And we've got catalytic osmium tetroxide and NMO. Those are syn dihydroxylation conditions. So we're going to add an OH group to each carbon of the alkene. But here we have a big syn versus anti issue, and we want to make sure to respect the stereochemistry here, since we're going to be generating some new stereocenters once we add those OH groups. So we can start just by drawing the backbone here without those carbons that bear the hydroxyl groups, and it's key, because this reaction is syn, to add those hydroxyl groups to the same side of the alkene carbons, which are here and here. So to do that, for example, we could put both OH groups on wedges, both pointed out towards us, noting that we have the zigzag of the backbone the same, the way we drew it, as it was in the original alkene provided. That's actually key. So we have both OH groups on the same side of the original alkene in this structure. Of course, at the same time, the two OH groups could add from the opposite side underneath the alkene, and in that case, we would get this product, which is not the same as this. These two are enantiomers, and here we've got an achiral alkene, achiral reaction conditions. We'd expect a racemic mixture of these two enantiomers, and that's important to note in this reaction, that we're going to expect this chiral compound and its enantiomer in equal amounts. Here we have a 1,2 disubstituted alkene reacting first with a per-carboxylic acid. We can tell this is a per acid because there are 3 oxygens. CO3H indicates a per-carboxylic acid, followed by aqueous acid, H3O+, and water is implicit in those reaction conditions as well. While we don't have to draw the result of the first step, it helps here to think about what we get after the first step and what happens mechanistically in the second step, particularly with respect to the stereochemistry. What's happening here is epoxidation followed by hydrolysis or ring opening of the epoxide by the acidic water conditions. The overall result is anti-dihydroxylation. Rather than going right to the dihydroxylated products, let's actually draw the epoxides that can form and think about how they might open. So the per acid is going to plop an oxygen atom onto the alkene either above or below the plane of the screen, giving rise to these two enantiomeric alkenes. And notice that because epoxidation is itself a syn method, both carbon-oxygen bonds form at the same time. We have two CO bonds on wedges in one enantiomer and two CO bonds on dashes in the other enantiomer. And the methyl and ethyl groups are trans in both of these. The trans relationship in the starting alkene is preserved in the epoxide products. In the second step, ring opening of the epoxide occurs with inversion of configuration. So we can end up, for example, if water attacks here, we end up with this product with this OH group behind the plane of the screen and this OH group above the plane of the screen. But if we imagine water attacking the other carbon, for example, attacking here, we could end up with the enantiomer of this structure. And in fact, there are 4 different ways water could open these two epoxide rings, and the only possible products are these two enantiomers. That's worth actually pausing and checking on your own that no matter which carbon we add to in either of these epoxides, we get one of these two enantiomers. Only the anti-products, none of the syn dihydroxylation products are observed. Here we're asked to supply the reagents we'd use to accomplish each of these transformations, and this is a key skill in solving multi-step synthesis problems as well, knowing the actual chemical compounds that are needed to effect a transformation that you want to do in the midst of a multi-step synthesis. This first example is actually not an alkene addition, but an elimination. We're converting an alkyl halide into an alkene. That's the reverse of addition. So we need to use some kind of elimination conditions here, and notice that what's desired is elimination of this hydrogen in blue, not the more substituted CH, but the less substituted CH. This corresponds to what we call Hofmann elimination, and to achieve Hofmann elimination, we need to use a sterically bulky base, something like potassium tert butoxide in tert butanol. In the second case here, we now have an addition. We have an alkene going to an alcohol, and the net result is hydration, the addition of the elements of water, H, there's a new H here, and OH right there, to the starting alkene. And the hydroxyl group ends up linked to the less substituted carbon. So this is an anti-Markovnikov hydration. We do anti-Markovnikov hydration using hydroboration oxidation conditions. So first a borane, something like BH3THF, and then sodium hydroxide and hydrogen peroxide to convert the boron group into OH as usual. And notice this would give a racemic mixture of this alcohol and its enantiomer. One thing I'll point out is that this carbon is not a stereocenter, since it's got 2 copies of the same group linked to it, essentially. In this third case in the bottom left, we again have a hydration that's an anti-Markovnikov hydration of the starting alkene. We should also notice that the H and OH are syn in this product, so H and OH add to the same side of the starting alkene. Thankfully, hydroboration hits both of these points, the regiochemical and the stereochemical, so we can again use BH3THF followed by sodium hydroxide and hydrogen peroxide to do anti-Markovnikov hydration of this alkene with syn installation of the new H and OH. And here again, we're going to get this plus the enantiomer, which is derived from essentially approach of the H and OH above the plane of the starting alkene as opposed to below in this product. Finally here we have the conversion of an alkene into an alkane, and this corresponds to a hydrogenation reaction. We can do this using hydrogen gas in the presence of a metal catalyst, palladium or platinum. So something along these lines would accomplish this transformation, adding 2 new hydrogens to the alkene to produce an alkane. At this point, our synthetic toolbox is quite limited, and more often than not, when we talk about synthesis, it's going to require multiple reactions, multiple steps to accomplish a given transformation. For example, we've seen no reaction that can cause a rearrangement of chlorine like this within a carbon skeleton. We're going to need to use multiple chemical reactions to accomplish this. And quite frequently, going through an alkene is a good strategy. We can eliminate off the groups that we want to remove, and we can add back in the groups we want to add, potentially at different positions, by doing, for example, Markovnikov versus anti-Markovnikov things. So here, for example, what we could do is imagine eliminating the chlorine first, eliminating in a Zaitsev sense HCl from this starting alkyl halide, going through an alkene, and then adding HCl in a Markovnikov sense now. Notice chlorine is linked to the more substituted carbon in the target to get this desired target alkyl halide. And that's going to involve going through an alkene like this via a Zaitsev elimination. So the reagents we would use here, something like a strong base and E2 elimination would work fantastically as long as the base wasn't too bulky, right? So something like sodium hydroxide and heat gives us this alkene, and we can convert that alkene into the more substituted Markovnikov alkyl halide just by treatment with HCl. This will protonate the alkene, we get the tertiary carbocation, chloride adds in, and we get this more substituted alkyl halide. So a two-step synthesis overall, but it makes an important point that we could not do this with a single chemical reaction. We needed two steps, elimination followed by addition, showing the power of alkenes for multi-step synthesis. Really, you can eliminate off a group you don't want and add in a group you do want in the right position, taking advantage of regioselectivity of many of these alkene addition reactions. In this second case, we've got a bromine in the starting material and a hydroxyl group in the target. We want to get rid of that bromine, eliminate off that bromine, and add in the OH group. Particularly adding in the OH group at the less substituted position is what we want to do. So elimination here, addition there, and the addition is anti-Markovnikov, and the elimination needs to be a Hofmann elimination, right? We need to establish a double bond here so that we have that double bond there for the anti-Markovnikov hydration that we want to do to install this hydroxyl group. So to achieve that Hofmann elimination, we need to use a bulky base, something like tert butoxide and heat, to give the less substituted alkene, and then to install H and OH in an anti-Markovnikov way, we need to use hydroboration oxidation, BH3THF, followed by sodium hydroxide and hydrogen peroxide. And again here, there's no way in a single reaction to go from this alkyl halide to this alcohol. There's no known reaction even that can do this in a single element, single reaction step. We need two steps to do this, two reactions. We need first to eliminate off what we don't want, and then to add in what we do want.